Today we're going to talk about inference in first-order logic. So we've seen that first-order logic, or predicate logic, is much more expressive than propositional logic. In predicate logic, I can write one sentence that applies to a whole universe of individual objects. So I can say something like, for all x, something x is round, if x is a ball. Of course, we could have written this implication the other way, too. We could have said, if something is a ball, then it's round. So that's a pretty natural kind of thing to say. And then I could say something like, thing t1, the constant t1 is a ball. And you and I could probably put together a proof that would show that the thing t1 is round. So I bring this up to sort of highlight the power of predicate logic. And it may seem that you could do something similar in propositional logic, so I could certainly create a proposition that looks like all balls round, right? So this is a proposition, takes on the value true or false, and we're sort of interpreting it to mean that all balls are round, which seems like it's saying the same thing as this predicate logic statement. And it sort of is, but it's not as useful for doing for actually reasoning with, right? So I could even say something like T1 is a ball and all balls are round. Therefore, T1 is round. And that's fine. So of course the problem with this is that I have to express this relationship separately for every ball in the world, right? So if I want to talk about T2, I can't immediately apply this fact to T2. I have to build another sentence in my logic base that says T1 is a ball and all balls are round implies that T2 is round. And that's not the case if I'm using predicate logic, right? So in predicate logic, if I add T2, this fact about T2 to my knowledge base, then I can immediately apply this piece of information, because this universal quantifier says that it's true of everything, to T2, and then I can draw conclusions about T2 as well. So that's the power of predicate logic, right? That's why we might prefer to use predicate logic as a knowledge representation formalism for AI. So we agree that it's more powerful. The question then becomes, can we do inference with it? And you know that we can, right? So you've taken a discrete math course, and one of the things that you probably did in that course is proof with predicate logic. So universal instantiation, existential instantiation, modus ponens, a whole set of identities that would allow you to prove whatever you'd like to prove from a particular knowledge base. But remember, what we want from an AI point of view is for a machine to be able to draw conclusions, right? So we want to be able to feed in a knowledge base of information that we believe to be true, and then turn the crank, and the machine should be able to tell us, what follows from that knowledge base. So we're interested in automating this process of inference. And one possible approach might be to take that big bag of inference rules that you learned in your discrete math course and somehow turn that into a search procedure, right? A search algorithm that picks among those different inference rules as actions and then moves to new entries in the knowledge base. And it's possible to do that, but that's not the approach that we're going to take. So the good news is that pretty much everything we learned about inference in propositional logic is going to transfer to predicate logic. And we're going to face the same trade-offs. So when we talked about doing inference in propositional logic, it turned out that general inference was NP complete. So we had an algorithm for it, right? We talked about resolution theorem proving, where we converted everything into conjunctive normal form, and then we applied this resolution inference rule. And so this was a nice mechanical way to do inference in propositional logic. It always works. It's easy to program, relatively, because there's only one inference rule to worry about. So, of course, the drawback is that because inference in propositional logic is NP-complete, our resolution theorem prover may not actually finish a particular proof before we die of old age. So the alternative that we looked at, right, the trade-off that we made was to restrict ourselves to just propositional definite clauses. Right, and as a reminder, that was things, something like this, B and C, where we have only conjunctions on the right and only implications like this. So the advantage of restricting ourselves to these definite clauses is that it made inference tractable, right? So we saw a couple of different inference algorithms, bottom-up and top-down inference, and we did some examples of those, and those were both tractable, so we were able to sort of prove that we could make whatever proof we needed to make in a reasonable amount of time. So it turns out that both of those approaches extend to predicate logic. We'll be able to do, we can restrict ourselves to definite clauses, the predicate logic version of that, and then we'll be able to do efficient inference. Or we can do general inference using resolution theorem proving, and we can extend that to predicate logic as well. So in the next video, we'll look at extending top-down inference algorithm so that it can be applied to definite clauses that have variables and quantifiers, etc.